All right, so now I want to cover section 0.3, which is all about sets and set notation. So a set is a collection of any objects, okay? These objects may be countries, cities, years. Most common we're going to see numbers and letters or anything else. And each of these individual objects is called an element of the set. A set is often specified by a listing of its elements inside a pair of braces, and a set may also be specified by giving a description of its elements. So for example, I could have the set A, B, C, and I could say that A is an element of, we want to define our set. When we name them, we name it with a capital letter. So little a is an element of A. But a set could also be described by giving a description of its elements. I could have the set P such that it's all X as long as X is a prime. So this would be an infinite set, right? Because there are infinitely many primes. And X is an element of this set. X is prime. So I could say 7 is an element of P, but 4, that's supposed to be a 4. We'll turn it into an 8. There we go. 8 is not an element of P. And we're going to go over these symbols a little bit more. So here's some examples of sets. I have the set of the first 6 letters of the alphabet, the set of the first 6 even numbers. It's also neat to know that graphs of lines are sets. So the graph of AB, where AB are all the solutions on this line, i.e. the graph of this line. And this is a set with infinitely many elements, right? Because it goes on and on forever. It's true for all real numbers. So let's take a look at these two sets. So I have let's let set A be the years from 1998 to 2011 in which unemployment is at least 5%. And let's let B be the years from 1998 to 2011 in which inflation is at least 3%. So here we have sets A and B. So let's figure out what years are going to be in A. So I want the unemployment at least 5%. So we start at the top and we go down. Up here's one year where it's 5%. Here's another one. Here. Ooh, then it got really high. Gosh. Okay, so set A includes the years 2002 through 2005. Let me write these down. 2003, 2004, 2005, and then it also includes 2008 through 2011. So I've got 2008, 2009, 2010, and 2011, and we denote this with brackets. So set B is going to be the years let's change colors, from 1998 to 2011 in which inflation was at least 3%. So B, oh, that doesn't show up very well, does it? How about this? B, there we go, that's better. It's at least 3%. So we look at the inflation column, and I'm finding for when it's at least 3%. I'm just going to go ahead and circle it to make life easier to find. Ooh, that's a really low inflation rate. Not part of our set. So that gives me B is the years 2000, 2005, 2006, 2008, and 2011. If I have two sets, I can find their intersection. So given any two sets, A intersect B is the set of all elements in both A and B. Okay? So let's say I have two sets. Here I have A and, well, I have a bunch of sets. I have my U, which is my universal set. We're going to talk more about that later. I have A, B, C, and D. These are all subsets of our universal set. If I want to find A intersect C, I look at the elements in A and I look at the elements in C and I see where they overlap. So C doesn't have a 1, but A does. That's not what they have in common. They both have 3s and they both have 9s. So where they intersect, where they overlap, is going to be 3, 9. If I look at sets B and D, B and D have nothing in common. So their intersection is going to be the null set, also called the empty set, and we denote it with this 0 with a slash through it. It's also important to know that any subset intersect with the universal set is just going to give us back that subset. If you see, the universal set contains all the elements in B, so their intersection is B, which is 3, 7, 9. So that's how a set intersection works. The union of sets is when I take my sets and I union together all the elements in A and all the elements in B. And if the element is in both A or B, we just write it once, right? Because it's only in our universal set once. So let's look at A union D. I got to take all the elements in A. So I've got 1, 3, 5, 7, 9, 11. Okay, and then I go to D and I'm like, okay, I've already got a 1. Okay, I've already got a 9, but I don't have a 13, so I can add that to my set. What's really interesting is that now A union D gives us the universal set, so we could also write it like that. Next, I'm going to take B union C. I look at B, I look at C, and I select what they have in common. Nope, I don't select what they have in common. That's an intersection. I'm going to select every element of B. So that gives me 1, 3, 7, 9. And then I have to make sure I have all the elements in C. So I have 3, 9, but I need 11. So that's my set of B union C. Next, I need to take a look at D union the universal set. Now, it's important to note that all the elements in D came from the universal set because they're a subset. So this is just going to be equal to U again. So here's our example from the previous example. Remember, this was unemployment levels and this was interest rates. I want to find A union B. So that's going to be taking all the elements of A and all the elements of B, and then I want to find their intersection as well. So I've got the year 2000, 2002. Typically we want to write these in order for clarity. 2003, 2004, 2005, 2006, 2008, 2009, 2010, and 2011. This is our union. If I'm going to take the intersection, I've got to look what they have in common. Well, they both have a 2005, they both have a 2008, and they both have a 2011. So their intersection is just going to be those 3 years. A set B is called a subset of A, provided that every element of B is also an element of A. It's also important to know, as I talked about earlier, the set that contains no elements is called the empty set or null set, and we write it like this. And that the empty set is a subset of every set. It's possible to have a subset with no elements. So for example, let's find all possible subsets of A, B, C. So because this is a set with 3 elements, I can have subsets of the empty set, sets with 1 element, sets with 2 elements, remember we separate them with a comma, or sets with 3 elements. So here we have all the subsets of A, B, C. It's important to note that the set BC is the same as the set CB. It contains the exact same elements, which is why we don't need to write this way. We'll write it twice. So we have all the subsets, like I said. Oops. The set U, as I mentioned, the universal set, is the set that contains all the elements in the set being discussed. Okay? If A is a subset of U, the set of elements in U that are not in A is called the complement of A, and we denote that by A prime. That's how we say this. This is said A prime. So let's let our universal set be A, B, C, D, E, F, G. Very creative, I know. And let's let S equal ABC. So what's S prime? Well, S prime is going to be everything in U that's not in S. So what's in U that's not in S? D, E, F, G. Let's let set T be ACD. ACD has the complement B, E, F, G. Now, I want to find S intersection T, the complement of that. So first let's find S intersection T. Where do S and T intersect? Well, they intersect at A and C. Now, if I want to take the complement of AC, that's going to be everything in U that's not in S intersect T. So that gives me B, D, E, F, G. Let me put brackets around that. Just checking our answers. So if S is any set, we denote the number of elements in the set by N of S. This is sometimes the cardinality. So for example, the size of the set S is 3. If S is the empty set, then it has no elements in it, so its size is 0. If I have the size of the union of S and T, that's going to be the size of S plus the size of T minus their intersection, because we don't want to double count. This prevents double counting. So we can use the inclusion-exclusion principle to solve this. So I want to know the size of S union T equals the size of S plus the size of T minus the size of the intersection. And this is what I want to know. I want to know the intersection. And means intersection. Well, I'm given those who have any sort of degree. This is S union T. So 310 equals N of S, which is those who had an undergraduate degree, which is 238 plus 184 minus whatever my intersection is. So I can go ahead and solve this. So I'm going to take 238 plus 184. That gives me 422. So I have 310 equals 422 minus intersection T. I'm going to subtract 422 from both sides. That gives me a negative 112 equals negative in S union T. I can divide both sides by negative 1. So I find that I have 112 presidents who had a degree in both, who had undergraduate and graduate degrees in business. A Venn diagram is a drawing that represents sets geometrically. So to construct a Venn diagram, you draw a rectangle, okay? And this rectangle contains the elements of U. You then draw a circle for each set. So this would be like 2 sets, A and B. And where they overlap, this is A intersect B. So here's all the possible ways. So we've got A union B, A intersect B, all the elements in the complement of A, all the elements in A intersect the complement of B, and so forth. I just wanted to show you the different things that could be represented with Venn diagrams. So let's draw a Venn diagram, with 3 sets, and then I want to shade the area that intersects and that represents R intersection S intersection T, R union S union T, and S intersection R complement intersection T complement. So this is going to be a little complicated. So let's draw a Venn diagram. So we can tell I'm not the best artist. Okay, so here's our Venn diagram. We've got our universal set. We've got R, S, T. Now, the section represented by R intersect S intersect T, we're going to label that in green. That's going to be this middle section right here. This is where all three overlap. So that's going to be R intersect S intersect T. Now, what if I want R union S union T? Well, that's going to be all of R, all of S, and all of T. So it's going to be all of this orange right here. Now, what if I want to know S intersection R complement intersection T complement? Woof. So remember, T complement, sorry guys, let's do some light highlighting. That might make it easier to get rid of should we make a mistake. So S intersect R complement intersect T complement. So here I know where S is. R complement is everything not in R. So it's going to be like all of this is R complement. And then T complement is everything not in T. So everything not in T. So it looks like the only area it's going to be is here. It's S intersect the complement of, we're going to do this in red. No, we're not. We're going to do it in black. So if I've got all of R complement, S complement, and S, this is going to be, this area right here of S is going to be the only section included in this intersection. And you feel free to sketch this out on your own paper. Make sure you have an eraser handy. I definitely always recommend sketching out Venn diagrams. That's like my number one tip. So let's talk about De Morgan's laws. De Morgan's laws say that if I have S union T complement, that's the same as S complement intersect T complement. And if I have S intersect T complement, that's the same as S union T complement. I just want that to be up here, okay? I.e., the complement of a union, you form the complements of the individual sets and change the unions to intersections. Or to find the complement of an intersection, you form the complements of the individual sets and change the unions to intersections, right? Complements, kind of like negation, you flip the sign. So let's prove De Morgan's laws. So if I have S union T, this is where S union T is, okay? It is, sorry, that's S intersection T. If I have S union T, that's going to be all of S and all of T. So if I take the complement in red right here, that's going to be all of this. All of this. Everything that's not an S union T. That's going to be the same as the complement of S intersected with the complement of T. Let me show you why. So this red right now, that's our union. So what if I take, first I'm going to clear all pen markings. If I take S prime, that's everything not an S. So that's going to be all of this. All of this. And if I take T complement, that's going to be everything not in T. So that's going to be all of this. All of this. So the question is, where is there both green and orange? Well, there's only both green and orange, where I'm going to highlight in pink, which is all of this beautiful space right here, which, as you can see, was the same as what we had highlighted in red before for the S union T complement. So that's De Morgan's law and why it works. I'm going to leave this one for you guys to solve on your own.